Okay, so this video is about manifolds. Now, a manifold, loosely speaking, a smooth manifold is just a collection of points that locally resembles Euclidean space. A lot of words. I'm going to handle it a little more simply. Okay, we're going to go to the go-to manifold, Earth. Earth is a manifold. Okay, and what we're going to do is we're going to tell the story of Steve. I know that's a crappy drawing, by the way. Steve is a Tejas Indian. I had to look this up. Tejas Native American, excuse me. Tejas Native American. And he lives in what is now currently called the town of Lubbock, Texas. Okay, so this is before any astronomy would have been around, or any astronomy that would have pointed to the fact that the Earth was round, okay, or anything of that nature. What we have is we have a kind of a Native American guy, and he lives on the flattest place ever, and he would be totally forgiven, okay, for believing that the Earth was flat. All right, so we're gonna draw here. We're gonna draw this little plane where old Steve-O lives here. So here he is. Hello. There's Steve. Okay, and he's standing here at point P. Okay, and Steve, he's probably thinking to himself, like, man, this is such a flat planet. If he's ever seen anything other than that, he's like, my God, this is some seriously flat land. Maybe he doesn't know anything different. Maybe he just thinks the whole planet looks like this, like it's just one big cap rock, And Steve, when he's walking around on this plane, what he can do is, he can go in any kind of direction he wants. Maybe he can leisurely walk this way, or he can run this way, or he can, sidestep it real slow, or he can do a real fast crab walk or something in this direction. Who knows? But let's say, for just argument's sake, that this is north and south, and this is the direction that Steve is pointing right now. That's where he's oriented. Okay, we can kind of take a snapshot of Steve at point P. Okay, and we can bring it over here. Okay, and what does this look like? Here's Steve. He's standing at point P, which is the origin in this map. Okay, and here's, let's call this I with a little hat on it and J with a little hat on it. Steve can go in any direction, right? Any direction, any angle that you choose, he could go in that direction. He could run over here, or he could take a leisurely walk back this way, or a leisurely walk back this way, or he could kind of, walk at a moderate speed over here. I could keep going forever. He could go in any direction at whatever magnitude is possible for Steve, his max speed, so to speak. That's actually another interesting topic. But what this is within the bounds of Steve's max speed, let's imagine that he could go in infinite speed. This is very similar to another notion that we have in math, okay, where I could choose any value x in the I direction, going this way, plus any value y in the j direction, going this way, and the combination of those two would represent any direction. Okay, so for instance, here's 1i, right, and this would be 1. Here's 1j. Okay, here is 1i plus 1j. It would be right here, 1i plus 1j. This is just a vector space, okay? This is a vector space, and the set of all of these things, where x and y are just real numbers, is called r squared, okay? So what we've just established is that Steve, in all the different ways that he can move, is the same as r squared. So we have to come up with a name for this concept of Steve and everywhere he can move on Earth from point P. And we call that TP of Earth. And this is actually formally called the tangent space. Right? Now, why don't we just map this whole thing out like r squared? Well, I'll tell you why. Let's say that Steve starts at point P, and he walks 500 miles in one direction. Okay? He thinks, in his mind, that he's on the ground walking in one straight direction. What's actually happening is if he were going straight for 500 miles, the Earth would slowly curve below him. And he would be at some crazy altitude by the time he actually did make it 500 miles away. It would be a considerable altitude, too. He might be out in the middle of space somewhere. What he's actually doing is, as he's walking, gravity is pulling him downward, so that he walks 500 miles in length over this surface. And that's the reason why, when we talk about manifolds, we're always talking about length, arc length, or what we call ds, which I won't get into, but let's keep going with Stevie Boy. So let's say he's at point P, and here's this tree, which I imagine would have been pretty rare in pre-Western Lubbock, Texas. And let's say that he wants to walk over to this tree, okay? So he wants to wind up here. Well, look, being at P is great and all, okay? And the vector space at P is great and all. But you notice these are just arrows. They're just telling me what direction he's walking and how fast he's walking from point P. What he has to do is he has to physically take steps. So he lifts one foot off the ground and plants it at point P1. Lifts the other foot off the ground, plants it at point P2. Lifts the other foot off the ground, plants it at point P3, right? Bada bing, bada boom, eventually he's going to wind up at the tree. Okay? Now at each point here, we have a different tangent space. Okay? And so on and so forth, all the way until he gets to the tree. And here's T tree of Earth. So this is the tangent space when he finally makes it. That's his destination. But let's say that his girlfriend is over here, and she comes out of the woodwork and she's like, "Yo, Stevie Boy," and he's at point 3, and he was gonna go to the tree, but now he's like, she gives him the wink and the nod or whatever, so he sprints over to her, right? Well, what he did was he stopped at TP3, and he changed direction. So he picked another element of TP3. This is also an element of TP3. He changed direction, and now he's going to her. Okay? So TP3, TP2, TP1, TP, they contain all the directions at which you can move, from which you could move, which you could move from P whatever. Okay? At P2, he could change directions too. At P1, he could change directions. So if you want to talk about paths and what Steve is actually doing, you don't care so much about this tangent space, or where he can go from P1, or, his speed and direction from P1. What you really care about is the collection of all of these tangent spaces. Okay? The collection of all of these tangent spaces is called T Earth. Now for a generic manifold, we would call this Tm, and we would call this Tp of M. So just the tangent space at the point P of the manifold M, and this is called the tangent bundle. Okay? Now again, at each point here, Steve's not really walking in an exactly straight line. He's walking in an approximately straight line. He's actually wrapping himself around the curvature of the Earth. Okay? That's important to remember, because that's the whole point. The whole reason we do this. So you have a tangent bundle, and that's all of these different points along with their tangent spaces, and that's where paths really kind of dwell. So for Steve to get from here to here, he needs tangent spaces, but more importantly, he needs tangent bundles. Now let's talk about why this is a manifold. Earlier I said that manifolds, roughly, or smooth manifolds I should say, they're roughly spaces whose tangent spaces are the same as planes. Okay? Well, here the tangent spaces are r squared. That works fine. Okay? So let's do a couple more examples of a manifold aside from Steve and Earth. Earth is clearly a manifold because anywhere, maybe I'll just restate this. Earth is a manifold because anywhere you look, if you're in the ocean, even if you're on Mount Everest, unless you're at some really sharp edge, you can zoom in and you'll get a plane, okay? So here's another example of a manifold. I like the way that topologists draw donuts, by the way. They taught me how to draw a donut correctly. I never did it before. Always did something funky, super elaborate, but this is easy. You do the big smiley, smaller upside down smiley, and then a kind of oval looking thing. And it looks like a donut. So anyway, this is a donut, or a torus, as we call it. And maybe I'll make this side solid, that side's a little dotted. Okay, and then there's another circle around here. This is called a torus, or a donut. Okay, and what this is it's S1 times S1. Now what is S1? And you could probably put these up as superscripts instead of subscripts. Let's do that. This is just a circle, and this is just a circle. Okay, so maybe going back to this example before moving on, Earth is an example of S2, which is a sphere in 3 space, but the reason we use 2 is because the tangent space, remember Steve, think of Steve living in Lubbock, Texas. Steve living in Lubbock, Texas, and the way that he can move is r squared. It's not r cubed, so we don't put a 3 there, we put a 2. This is an example of what gives you a 2-dimensional tangent space. Okay? The torus, or donut, is a circle. We use S1. Remember, the sphere was S2, circle's S1. A circle times a circle. Okay? And this is, we're using the idea of a product here. Okay? In other words, I'm taking this circle, and I'm gluing circles at every point that go around the torus, okay? So I'd have a circle here, I'd have a circle here, I'd have a circle going through that point, and that point, and that point, and on the other side, too. And that gives me this torus. Alternatively, I could just take a big circle around the whole thing and wrap little circles all the way around. I would get the same shape either way. That's why we say circle, product, circle, okay? This is a torus. This is also a manifold, and if we look at this, we zoom in real close, we get something that looks identical to what Steve-O would see. So let this be a lesson for you. If you ever wake up on a random planet, don't just assume that it's spherical because it looks flat. Might be a torus, although I don't know if that's possible or not. But you can't make assumptions, is what I'm saying. Now, yes, right. So this is the same thing. This is that plane we looked at before. This is the r squared vector space. Now Steve's idea, by the way, that the Earth must be flat is based on his positioning. Okay? What he's saying is, well, everything around me is flat, and if I can walk in one direction, I feel like I'm walking in a straight line. This is obviously not true. Earth is that 2-sphere, okay, which is not isomorphic to it, to the r squared. But his tangent space, from his perspective, it is isomorphic to r squared. And going back to this example, if you want to do calculus, you have to consider the curvature of the Earth. If you want to go great distances, you do have to consider the curvature of the Earth. It's another reason why if you wanted to get from, say, New York over to England, what you're actually doing is you're going over a great circle. You're not going over a line, right? You're going over the shortest geodesic. Anyway, another example of a manifold. This is a topological manifold. This is not a smooth manifold. And see if you can figure out why. If I took P to be this little point here, then my tangent space, if that's P, my tangent space of this cube would be exactly r squared. It wouldn't even be an approximation. It would be exactly r squared. But But suppose that I looked at this point, Q, right over here. What would I see? Well, this would look like this, with three weird sides, right? And it would not, this is not r squared. So because these edges are discontinuous, I can't move from one to the other as a plane, this is not a smooth manifold. See if you can figure out what we could do to this cube manifold. What we could do to this cube to make it a manifold. Okay. I think that's all I want to say. All right, peace, dogs.